All right, we're excited to introduce our next keynote speaker on satellite detection of global methane emissions. Please welcome Professor Stephen Wofsy, Professor of Atmospheric and Environmental Science at Harvard University.
Hello, everybody. My name is Stephen Wofsy from Harvard University, and I'm here today to discuss with you how we measure emissions of methane from human-driven sources using a new class of satellite sensors. The sensor that I'm going to be telling you about is called MethaneSat. It's part of a totally crazy research and development project that I've been taking part in for several years. It is currently funded by MethaneSat LLC, which is a wholly owned subsidiary of the Environmental Defense Fund. So it's a private enterprise operation. We'll talk a little more about that in a moment. First of all, let me discuss what we measure when we measure methane concentrations from space. We look at the ground, we look at reflected sunlight from the ground, and we take apart the spectrum in the shortwave infrared and infer the concentration of methane in the total column of air relative to the total column of dry air. So, for example, if I were to have a source of methane that doubles the amount of methane in the boundary layer near the surface of the Earth, lowest kilometer, if I double that concentration, the sensor looking down in this way will see a change of about 7%. So I'll talk a little bit more about that also. The good thing about this measure is that it's a direct indication of the mass of methane that's been added to a column of air. When you make a point measurement within the atmosphere, you don't know how much air has been affected, so it's very hard to compute the mass that's been added, but you can do that very easily with this type of measurement. There are existing satellites that measure methane from space, and currently they're in two different types. One is a global mapper. The Tropomi satellite from Europe is an example of that. It measures everywhere on the surface of the Earth that it can see through the clouds every day. It has a fairly large pixel size, 5 by 7 kilometers. We'll talk about that in a moment also. And then there are what we call point source detectors. They have much finer spatial resolution, but the trade-off there is that they're much less sensitive to added methane, and so they only see very, very large emission sources. So Tropomi has been up there since 2018 or so. It's a really interesting system. It measures at low spatial resolution that I mentioned. It has high precision, and it can produce maps like this. This is a monthly average map of methane concentrations in the atmosphere. If you average this over long periods of time, you can begin to see patterns that tell you about very large-scale emissions, and you can infer what they are. You can also see very, very large point sources, but you have to be able to fill up several of those 5 by 7 kilometer pixels in order to see it. Here's an example of a point source measurement that it did make, and you can see from the map here that they're plotting emissions of order 150 tons per hour or of that order, very, very large sources. During the time that they have been in orbit, let's say for over a 2-year period, they see about 600 of these, and there are 1,200 detections over this 2 years. So then the other type of remote sensing measurement, the point source mapping. Here's an example by the Carbon Mapper, which is an airborne system. Also, Sentinel-2 and EMIT satellites platforms can do this. They can see very, very strong plumes, and that's all they can see. They can map them pretty well, but you can see the scale here is 100 meters instead of the whole global scale that I just showed you. And you can also look at the concentration scale. This represents increasing the concentration in the boundary layer by more like a factor of 5 rather than doubling it, and they divide up their concentration scale into 4 crude units, but it is a good way to measure emissions from strong sources. Now, what about methane sat? So methane sat is very different. It's a small sat, not a huge thing like Tropomi and some of the other satellites. And it measures concentrations in a region about 250 kilometers on a side, and in that region, it has very fine spatial resolution and very high precision. So it measures this wide swath, which will basically cover an oil and gas production area in one go. It will be measuring 30 or so of these a day starting in January of 2024 after it's launched. There's also an airborne version of this, Methane Air, which we've been flying since 2019. I'm going to show you some results from that. I'm going to skip over this, but if you want to if you're interested in the technical parts, take a screenshot of that. That tells you how we managed to get this fine resolution and such. Okay, here's an example of flights taken over the Permian or the Delaware Basin in the Permian region of Texas and on the Texas-New Mexico border. You can see the concentrations there are shown down here. This is looking at really just a few percent change in the total methane in the atmosphere, but you can plainly see a lot going on in the Delaware Basin. Here you have a gas processing plant, the Mavita gas processing plant in Barstow, Texas. This pixel on the right here has been degraded to look like the satellite, even though the resolution of the airborne system is much finer. And you can also see lots and lots of other things going on here. And what do you do with information like that? I mean, this is really beautiful. I put it on my wall. We want actionable data. We want data that's actually going to lead to mitigation of this type of thing. And when you have such fine detail and such high precision, you can actually just take this apart. So here again is the same image I just showed you, but we've subtracted a background amount. And this is showing, you know, what we just saw. And then at the top here, we have an assessment of the emissions made using atmospheric model with observed winds, plus that concentration map that I showed you. And you can see here basically 2 types of sources. The point sources are indicated by these little dots here, and the area sources are indicated by this heat map. And this is something that nobody has been able to do previously, and you begin to now get the sense, what is the balance between the very large point sources and area sources, which are basically innumerable, much smaller emissions from all over the place. And this really allows us to home in on where these emissions are happening, both the point sources and the area sources, and begin to think about how to remediate them. First, we have to understand why they're happening. And this type of data will really help us to understand that. This map over here is showing the simulation of the observations once we have put in what we have retrieved as the emissions. You can see it's quite good. There's a little bit of differences down here, for example, which has to do with the fact that the wind field that we have to use from meteorological model isn't perfect. You can even use this system to do some probing of what you might call environmental equity. So this is a map of methane concentrations in the Salt Lake City region made by the Methane Air aircraft version. You can see little patches where their methane is higher than in the surrounding area. And then you see a number of places where it's quite a bit higher. So up there in Bountiful, and then over here, these 2 on the left are landfills. And this part over here is well, what is it? Let's go see. So home in on it. Now I've taken away most of the background of the methane concentrations, and I've just overlaid them on a Google Earth image of the the region. And okay, so there's something going on there. Well, what is it? And you can see that the high methane concentrations are associated with an industrial complex, a petrochemical complex. There's two of them, one here, one here. There's a bunch of pipelines running through here, and there are people living here. Now, methane by itself isn't really a toxic substance at the concentrations that we're looking at, but this is not a natural gas plant. This is a petrochemical plant. So these methane emissions are associated with volatile organic compounds and such, and this basically serves as a tracer of what's happening. If you go into this neighborhood, you see there's a lot of pipelines going through there. Maybe they're not the best performing pipelines. So just a last word here about what the concept of the project is. We're undertaking this in order to change practice in industry so that these methane emissions don't occur. And so we're going to use these data to understand why they're occurring and to quantify them so that when people consider action to mitigate these emissions, that they're going after the places that are important and where the payoff will be significant. So it combines in one project this advanced science and engineering. When we started out to build this spectrometer, I thought we were building a fairly run-of-the-mill imaging spectrometer for space. It turned out, though, we actually had to push the technology pretty hard. All the data will be free and available to people. It'll be done in a timely manner. There is, of course, a lot of room for providing value-added products based on this. We are certainly trying to make the distribution as accessible to real people as we can, but there's going to be quite a limit to that. One of the reasons why this is being funded by private philanthropy is that you cannot really do advocacy, let's say, in a NASA framework. That's not their mandate. They won't do it. So somebody's got to do it. If you go into the other side of the private enterprise, so into a profit-making framework, that's all well and good, but that will certainly limit the impact to the practice that we're trying to affect. So we're really trying to have an impact there and to rapidly to use this this tool as a way to lead to rapid reduction of methane emissions to the atmosphere. So my little aphorism for this is that we're doing photons to boardroom. And so in the framework of the program, we have advocacy. We have people whose role it is to take the scientific product and make it actionable. And there, once again, wanted to remind you who is funding this. So to roll this up, MethaneSat and Methane Air represent a new generation of high-resolution satellite and aircraft remote sensing instruments. It's really true. It will be more. This one will be the first one. It really promises a whole new level of insight into emissions in terms of both quantification and identifying where they are, et cetera. Methane emissions can be quantified from both point sources and regional diffuse emissions using these sensors. This is the special thing. That's what's new. Currently, there's really no sensor in that space. Finally, the data enable us to span this photons to boardroom paradigm that I've spoken of.
Thinking about the atmospheric trace gases like carbon dioxide, methane, and nitrous oxide that really make up the majority of greenhouse gases, how would you describe the role of methane relative to these other gases and contributing to the overall climate warming?
That's a really good question. Methane accounts for about 25% of the additional heating of the surface by the greenhouse gases that we put into the atmosphere. It has an atmospheric lifetime of about 10 years. So if we were to stop emitting all methane to the atmosphere, it would tend to reduce back to its pre-industrial value. Right now, we have about 3 times as much in the atmosphere as there was in the 18th century. And that would basically mitigate that 25% right off the bat. CO2 has a more complex cycle in the atmosphere, and you could roughly say it has a 100-year lifetime. So if we were somehow to stop emitting CO2, then it would take 100 years to go back to something close to what we have. I think more importantly is that methane emissions to the atmosphere aren't serving anybody's interest. It's not like somebody gains by emission to the atmosphere. Emit CO2 to the atmosphere, you're generating electric power, et cetera. There's many reasons why that's integral to our economy. So there's two reasons why mitigating methane is an attractive way to try to get a good start on mitigating greenhouse warming.
Makes a lot of sense. Now, I believe that in the past, Stanford researchers have looked at using spaceborne integrated path differential absorption LiDAR for global observation at day and night and over land and water surfaces. Can you tell us about some of the challenges of measuring CO2, CH4, and N2O from space?
Yeah, so let's start with what we're currently doing using reflected sunlight. Obviously, where it's dark, so in the Arctic in the winter, you will not be able to do that. To the extent that there are day-night differences in emissions, you may find it hard to quantify those. The good news about these methods, though, is that they are extendable down to the scales that we've just been talking about. We have not produced the Beth methane sensors that we can, and the same is actually true for CO2. And so you will see in the next 5 to 10 years a significant enhancement of the capabilities that we have in those areas. With respect to the LiDAR, it's the only way you're going to do it at night. Mm-hmm. But LiDAR is that's your real point sensor. It's got a width of 25 meters per shot, something like that, maybe 100 meters. So you get these little pinpricks all across your domain. You can certainly use this in very constructive ways to examine emissions, but it's going to face its challenges. And it hasn't been spaceborne LiDAR of this sort has not been created. I don't know of one on the board. There is one on the boards, but mostly it's been done in aircraft demonstrations.
Mm-hmm. Now, the main, I think, the advantage of methane SAT, aside from really many, is the ability to detect the diffuse methane or the plumes, and which is a game changer in itself. I wonder if you could give us some examples of maybe some preliminary data that shows some pretty substantial margins of errors, or maybe areas where it's been kind of surprising new discoveries because of methane SAT's new capabilities.
So currently we've only got about 20 flights of our system. We had some avionics issue, then there was a COVID epidemic. When we've done that, we've just found things all over the place that we weren't expecting. So, for example, in that Permian region, we went twice, once 2 days after the first time. The second day, there was a massive plume of methane coming out of an open field. There wasn't anything there. So we looked very closely at it and said, it looks like maybe there's a pipeline there. 2 weeks later, the company that owns that pipeline reported the pipeline break to the New Mexico government, and we estimated that they were emitting over that 2-week period somewhere between 5 and 10 tons of methane per hour. So that one instance was adding 10 to 20% to the total emission of that whole area. So that was a surprise. We also looked at some landfills. Landfills are another source of methane to the atmosphere. Some of them produce massive amounts of methane, others produce none at all. And the EPA has a reporting system for landfills. And if you make a plot, and this is also reflecting work by some of my colleagues at the University of Arizona, if you make a plot of methane emissions from these landfills against the EPA plot, there's no correlation at all. So there's a lot to be learned there.
And I think what's interesting is you had shared a slide where it showed how some of these plumes had encroached into residential areas where people are actually living. And what's the implications and what are the potential added benefit of having this capability for warning potential neighbors that could be affected and not even aware of it?
So that's a really good question. As I say, the methane concentrations that you see there they don't represent a fire hazard, although I'm not sure if I wanted to go near where the leaks were, maybe I would have a fire hazard. In the case of the petrochemical plant, that methane the concentrations will be correlated with volatile organic compounds. So the way that you could leverage that, let's say if you were a state agency, is go there and measure those correlations and then look to see where the methane is, and you'll figure out where your people are being exposed to hazardous chemicals.
Now, my understanding is that Methane SAT, the satellite, is expected to launch early next year. It's being built by Ball Aerospace and Blue Canyon Technologies, and will be launched via the Falcon 9, and then the Control Ops Center built by Rocket Labs. Is one satellite, in your opinion, sufficient to perform the task at hand? Because the goal of reducing global methane emissions by 45% by 2025 is pretty significant. And if you had the budget, what would be the ideal number of satellite constellation to provide the most actionable near real-time data?
So that's a really good question. We can look at any point on the Earth every 3 to 5 days. We can't cover the whole Earth. And we only look at one time of day. So in my mind, the ideal number would be something like 3. Then we could look at any point on the Earth every day. And we would also be able to begin to understand how these emissions are cycling through the workday. These things are not, people like to call them leaks, but most of what you're seeing is not leaks. So that pipeline leak I mentioned, that was certainly a leak, but a lot of it is happening due to either chronic emissions due to equipment that you have that's intended to emit methane as part of its operation, or part of it is just due to depressurizing systems that you need to work on or whatever. And all of that stuff can be remediated, although what you would do for the diffuse emissions in the mitigation area is pretty different from what you would do for the large events.
Yeah, it makes perfect sense. And I think there's an area that's really important, and I wish we had a little bit more time to discuss this, is the fact that the data that the project will generate will be free, a public good. And I find that both fascinating and compelling. And I wonder, again, I recognize this may not be in your wheelhouse, but if you could opine on how this data could be a gold mine for things like the carbon credit markets. And do you have any thoughts on how to architect incentive structure for profit maximizing or reducing or limiting methane sources, while potentially also applying a carbon tax on those entities freely spewing methane into the atmosphere?
So that's a really good question. This is not in my wheelhouse, but I do observe what people are talking about and doing. One of the things that has happened is that some countries and some companies and some investors have started to target investing in natural gas operations or buying natural gas from places that are clean. And so there's already been instances where major purchases of Permian derived gas were called off because the Permian is a huge leaker, as you could see from those images that I showed you. So I think there's a lot of possibility there. And the people at EDF are open to talking to people who are interested to see how we can help them to understand what will be available, what is coming online in the next year, so that they can begin to optimize their performance there.
All right, so I have one final question from the live stream from Blair. How much time from data capture to analysis is completed?
So in the case of the methane air, we expect to be able to get our first look data out in 3 days. In the case of the methane sat, it may take an additional day because of the time it's required to transmit the data down to the Earth and bring it to us. But we're talking about in the range of a week or less. That being said, that won't be what we will achieve right at the beginning. But we do have the infrastructure, the computing infrastructure, and the high throughput capability to process those data quickly. And that's what we intend to do. And we're also, because we have this airborne simulator, we're able to really hammer the algorithms and the treatment of the data very hard, so that initially when we hammered on it, it would break very quickly. Now we can pretty much rely on what we're getting, so those quick look data should be available in a short period.
Well, I want to thank Professor Wofsy for a terrific conversation on Methane SAT's goal of reducing global methane emissions. Please give him a round of applause. We're now going to transition to our space track.